Were you there?
No, I kept up with the score though, some of my friends did. They killed it.
I looked at the runs in 1-8. That's unheard of.
I think the final score was like 20-11 or something like that.
How many home runs?
I'm not sure, I know for a fact there was at least one, but I don't know how many others.
That's a really good.
Yeah, they're doing a little bit this year.
I'll leave 1 or 2 more minutes. I want to tell you, today, I want to start, I'm going to kind of try to combine a bunch of stuff about related to the Gaussian stuff, error functions and all that. Now, I was doing these things on my calculator, on my computer, and I was using a complementary error function to get all these things. I'm going to go through this with you. I want to tell you, Gaussian distribution is something that very closely models a lot of things, a lot of natural phenomena. I mean, all sorts of things, the molecular velocity distribution and Vx, Vy, and Vz, they fit a Gaussian curve perfectly. We get other stuff from, we get things called a Rayleigh distribution we're going to be talking about, and we get the Maxwell-Boltzmann distribution. So really the velocity of the gas where you get the energy, the average energy and temperature. So a whole lot of this stuff has direct implications. And, a lot of stuff to do.
For the quiz and stuff, are we gonna get the chart one?
Yeah,
Okay.
I mean, matter of fact,
Because the chart is the homework will to the point.
did you use a calculator to get this stuff?
No,
Do you-
I can do
I-
all the time.
I don't know for sure, but I think most modern calculators easily do these things using either, we're gonna go through the complementary error function. I don't know if they have the Q function all the time, but, they have functions that allow you to calculate easily. Do you have a modern calculator?
I can go buy one, but this one doesn't do that stuff.
You can use the tables if you want.
I like the tables.
I may, just do that to make it easy on you or anybody else. Let's see, I'll wait. And then I'll start. So here's what my plan is for today. I want to do a recap of some of the functions that I think are important in the area of Gaussian random variables. We're going to talk about, also talk about the nth central moment and how come if it's odd, it's 0. Well, I think I mentioned this. If it's even, there's a simple formula for it. We'll do some exercises. We'll talk about the Rayleigh distribution. And then after Rayleigh, I won't get into Maxwell-Boltzmann. I'll do the problems, because I think that's where we're going to capture a lot of this. We'll at least find out what we know and don't know by doing problems. Now, this is my own philosophy about most of this stuff. When I was sitting where you were in school, I did every problem that had an answer, and if I could, I'd get a solutions bank and try to compare it. And I always worked the problems, because I found this out about myself. That if I can work all the problems in sections, almost guaranteed I understood what it's about. Almost guaranteed, if I knew what I was doing. If I didn't understand things, there was pretty clear that there were things that I need to review, and I had to check on. And that's how I went through engineering, and even in graduate school. As much as, there's a lot of proofs and some stuff, but in order to do the proofs, you really had to understand how to do problems using theory. Anyways, that's my philosophy, so that's the reason I'm going to do it. So I'm going to start, this is all about Gaussian random variables. And first, the Gaussian, and some of this is review, you don't have to take notes here, just listen. So when we had Gaussian random variables, we had something where we had a density function, f of x. If x had a mean of that and a variance, or of, this would be a standard deviation of variance, sigma squared, it was equal to 1 over the square root of 2 pi, and then That's the variance, not the standard that's the standard deviation, not the variance, times exp to the minus, then it's the quantity x minus x bar, that's the mean value squared, over 2 sigma squared. That's the general Gaussian distribution, and it's a density function. So that density function is used to get a whole bunch of stuff. The first function is just a general probability that the random variable x is going to be, in this case, the way it's done is, I better do it this way. Random variable x greater than minus infinity, less than x. So this is going to be something where they take this density function, it'll be the integral from minus infinity to x of 1 over the square root of 2 pi sigma times exp to the minus quantity x minus x bar squared over 2 sigma squared. And frankly, I should have done this with a u and a u bar and then du, because you can't integrate, you can't have a limit here that has to do with the differential inside, but that's just, with engineers we do it all the time. I would integrate normally, if I was doing this by hand, in dx and just substitute that with x, the upper value. So that's the distribution function that we've been using. There's also a function that the book has tabulated, and its symbol is this. It's really phi of x, I guess, and that's equal to minus the integral, or the integral from, minus infinity to x of 1 over the square root of 2 pi. There is no variance in this one, exp to the minus, and this is just going to be u squared over 2 du. This is in the book, you don't have to worry about it. Here, this is really the normalized version of this. If you look, same exact form, it's just, sigma is assumed 1, would be assumed 1 over there, and the mean would be 0. Y'all follow me? That's just relationship. So the nice thing is that if you wanted to know f of x, or this, the probability that x is greater than minus infinity, less than some value of x, that's the distribution function, that's equal to simply this function evaluated at x minus the mean value over the standard deviation. Right? So that's the reason this is important. Now this is tabulated in the book, in the back, and you mentioned that you're going to use tables, so you know where that one is, right? Okay. Also, another thing I'm going to make mention of, because they don't have the negative values, and we found this out in the tables, that of minus x is equal to 1 minus this of x. So, I better use the same symbol. So, in other words, since they don't have the minus values tabulated, but the positive, you can calculate the value of the positive argument there and subtract that from 1 to get the negative argument. That's the whole trick. Okay. Then, okay. Now there's a complementary function to this, and it's called the Q function. I better make sure I define it. Q of x, and that is equal to simply 1 over the square root of 2 pi, and it's times the integral. But now the argument goes from x to infinity of exp to the minus u squared over 2 du. I'm going to make a comment here. If you look at this, you can see that this function plus that function has to be 1. Right, it has to be 1. So if you take this psi, I don't know if it's called phi. Actually, in the book, that's a capital, isn't it? It's not a phi, it's a capital symbol. And what would that be in Greek?
It just has the capital I in the middle.
Yeah, it's a Greek letter, and I should know this. I use small Greek letters most of the time. It might be iota, but I'm not sure. This of x plus q, this is q of x, equals 1, period. And they always will. Because the probability of something being less than a certain value and the probability of something being greater than a certain value, if it's a continuous function, has to be 1 because that the actual single value doesn't have meaning. Remember I said that the probability of the thing having a value from the density function of just a single value here, it's 0 because there's no area under the curve. Okay, so now that I've said all that, now I'm going to introduce some functions. And he does a few of them, but there's a lot of them. There's a function called the error function, ERF of x. Now this is typically on all your calculators. There's an error of x and ERFC of x. Error function of x is simply 2 over the square root of pi. And that's going to be the integral from 0 to x of e to the minus u squared du. The reason I'm telling you this one's always used, and you're going to see we can get the q function, all these other functions from this. The other one is the complementary error function, and that's equal to 2 over the square root of pi, but then the integral goes from x to infinity of e to the minus u squared du. And that's the complementary error function. Hold on. Yeah, that's right. And here I'm going to make mention of something. This from this complementary error function, the q of x, that right here, q of x is actually equal to 1/2 the complementary error function of x over square root of 2. You're going to see why that's important. Put that down here and start. And this is q of x. These two will be used all the time. Okay. Now, I think I got all these functions in the relationship. Okay. In the book, I'm just going to say this. We'll be talking about all of them. One of the things that I'm going to just state right now, you're going to find that all these functions are interrelated. If you want to do your calculations and use this, it will get you all these things. I've been using the ERFC of x. I can get all these other functions from it, and I'm going to show you that in a second. All right. So it's like you don't have to have a Q function and a density function like that. If you just look at this for a second, I can see. I can get f of x is really just this function here, but then the argument's modified to have x minus the mean over the standard deviation. This is normalized. If I take a look at this, that because the q function plus that function equal 1, I can use the actual q function to get that function or anything I want. And start that one. And now I'm going to tell you something about this q function, why it's probably more valuable than we think at first impression. Whenever we have, we're talking about evaluating this kind of a function where the probability is very, very small. Remember that q function is right there, over there. So I can say, this is in the book, he makes the statement that if you're talking for very small, or things with extremely small probability of occurring, then they can have upper and lower bounds on the q function. And they said 1 minus 1 over a squared times 1 over a square root of 2 pi, just bear with me on this, times e to the minus a squared over 2 is greater than or equal to q of a less than or equal to 1 over a square root of 2 pi times exp the minus a squared over 2. Now, what this does is it gives you the upper and lower possible bounds of q of a. Remember, for this function to be evaluated, it requires this integral to be actually done. Okay, all right? And that's something to be said here. This has no closed form solution, so it means the computer has to numerically evaluate, and that's why there's all that tabulated data in the back. But here's a bound on it. And it comes down to this, if the likelihood of this event is very small, then you can say, we can take the average value of these two and say, that's about what this is going to be. That's what they do in the book. I mean, if this is the upper bound, and this is the lower bound, all right, and this is for things that are very improbable, then the average value is a good guess to what Q of A is, and I checked this on some of them. Actually, it's pretty good. So it says, that means Q of A, and again, a very improbable, this is when all of a sudden things are not very likely. Matter of fact, this is for very small q of A. That's just the average value of that, so it's 1 minus 1 over 2a squared times 1 over a square root of 2 pi here, and that's going to be exp to the minus a squared over 2. All right. So here's an example of some of this stuff that I'm going to do. In the book, he has, I'm trying to find out what this is. On page 71, so I'll come over here and erase that part and then do this example. Now, it has an example where the mean value of x is 0.5. The I guess its variance, sigma squared is 0.2, and what they want is the probability of the random variable being greater than 2.5. So the average value is 0.5, the mean, this is Gaussian now, the variance is 0.2. Which means the standard deviation square root is 0.2. This is on page 71 if you want to follow in your book. All right. Now, technically, if we want to get the probability that the value is greater than 2.5, this has to do with the problem. I think he talks about a voltage here, where what he wants to do is he's looking for the possibility of triggering or the value of a voltage going above 2.5 volts. It says the average voltage is actually 0.5 volts, and the variance is 0.2. So, if I use the Q function right there, I would say the Q, now you replace x with the argument x minus x bar over sigma, or it would be the Q function of x, which is 2.5 minus average value 0.5 over the variance, over the standard deviation, which is square root of 0.2. Okay? I did this on the calculator, and I didn't put the number down. But if you do it he has it in the book. If you do this, this is really Q of 2 over the square root of 0.2. And I think that's Q of 7 point something, or 4.77. Can you take 2 over the square root of 2 for me, if you can do that for me?
0.41,
4 point what?
1.41,
2 over the square root of 0.2?
oh, 0.2, sorry. Yeah, 4.47.
4.47, all right? Now, if you do it using that Q function, or using this, do you have the ERFC in yours?
That's what I've been trying to look for, and I haven't seen it yet.
Pretty sure most calculators have the error function, the complementary error function. ERF or ERFC. If you don't have it, it's all right. But if you do this actually, and I did it, and I was using my laptop with MathCAD and just defining everything in terms of the error function. When you get this, the value is 3.875 times 10 to the minus 6. All right, that's small by any measure, right? A very small probability. Now, can you see it in your tables? I'm just trying to make sure. That would be an argument of 4.47 for the Q function.
And I got a table that says 0.3911 times 10 to the negative 5.
That's not Q though. Oh, it is, you got the Q function. And that's for
4.47.
maybe it's 4.477, is it?
4.472125.
Okay. And what do you get for that?
I got 0.3911 times 10 to the negative 5. That's what the table says for 4.47.
I think in the book, I got the answer in the book, and it's 3.875 times 10 to the minus 6.
Yeah, that's what the book says, but that's not what the table says.
That's weird.
Which is, yeah, that's.
Because I actually did this on my calculator too, and I got the right value.
Yeah, yeah.
What page is that table on? Okay.
435. But also the book says that Q equals 1 times 10 to the negative 8.
Well,
I'm
Four
Looking at the
percent.
same thing you are.
What was it?
yeah.
This is 1.0050 times 10 to the negative 8.
Yeah.
On page 72.
And that's the Q, which is like the 2.5 minus 0.5 over the standard deviation.
4.472.
Probability.
3.875 times 10 to the minus 6. Is that right? That's, oh, wait a second, I have that wrong.
Is that the probability to be bigger than 2.5? Is that?
Yeah.
Okay.
Yeah, if it's the Q, it is.
Yeah, the calculator spit out 3.875
Times 10 to the minus 6, that's what I got. All right, what page is Q on again?
435.
I'll just take a quick.
You got a probability and then normal CDF.
That's Q of 4.47.
But you don't have those, what you said about
You know, I got
charts.
I see that too. 0.875 0.3911 times 10 to the minus fifth, it looks like.
Even
This
as
is
a,
close,
yeah, it's off by a factor of
well,
10.
yeah.
I guess this is because, what is the exact value for this? 2 over square root of 2.
4.472135.
I bet you that's it, the round up. I mean, those tables, don't extend that far, so it's,
And 71, page 71, it says use the table in appendix E for the MATLAB with the value.
So then more or less
4.472.
approximating.
Yeah, I guess it just messes up the table.
yeah, you're gonna get a round up there. But I can tell you that I did this with MathCAD, and this is double precision. That answer's right there, that one. That, I guess the interpolation is the problem on that, on the tables, but, I'll level with you, if you're gonna blow money on a calculator, now's probably a good time, because you're gonna save yourself some headaches on those tables.
Yeah, I'm seeing that.
But, do you find that on your calculator or not?
What you got right there?
Yeah.
So you have to go into the probability menu and you'll select the normal CDF. You'll put in your lower bound, your upper bound, your mean, and
Standard deviation.
standard deviation.
Or variance, one of the two. But if your calculator has a manual, look at it, because all the modern calculators do these tables for you, so you don't have to rely on it. Now, a long time ago, before the calculator, what they did is they devised all these elaborate tables and expansions and stuff like this, and they had clever methods to estimate it. But the thing I wanted to point to is this bounds method right here. Now take a look at this. Remember, that's a very small number, but just look here. You don't need to calculate that number per se using an integral to get it exact. We know it's going to be about here. Just watch how this comes out. The argument A is equal to 2 over square root of 2, right? Or 4.4721, whatever it is. So put it down here. 1 minus 1 over, you got a calculator, you can do this. 2, and remember A here squared, A is that number, 4.472135. So that's what it is, square it, and then take 1 over square root of 2 pi times that number again, and then exp to the minus that number. I just don't want to write it over and over again, and see what you get. Can you do that for me? The reason I'm going to show you is it's a whole lot easier to do math. And back in the day when they didn't have, sophisticated calculators, see, calculators came on the scene about the time I went to college. But before that, when I was in high school, actually they were coming on, but around the time I was in grade school, everything was done with slide rules. You had to get you know what a slide rule is even? Anybody ever hear of it?
I've heard of it.
A slide rule is basically a ruler with a lot of moving parts you can pull apart, and they had it's a precision instrument, but you could do logarithms, you could do squaring, you could do everything super, super fast on that, and you get pretty good estimates if you had good eyes. But slide rules were the way they did it. Now, you can do that on a slide rule very quickly. You can't do that on a slide rule. I should show you guys this later this summer. Because I haven't used the slide rule, and I mean this in probably 30 years, 40 years maybe. But I've got one. Your grandfathers probably used slide rules, I think. Anyway, if you were in a shop and stuff like this, anybody that did anything where there's a lot of mathematics, like a draftsman, all this stuff, they would have slide rules to do a lot of calculations. They didn't have calculators.
My grandfather probably did music engineer,
Oh yeah.
Star Wars fan, back in the day.
With Reagan, that's calculators. Reagan was my president when I was in grad school. We loved him. When he got elected, they had a celebration at the hostages were freed out. It went crazy. It probably did here too. The media never covered it. And the whole campus went nuts.
It's really close.
Yeah. What is it?
It's a 3.948 times 10 to the 6.
3.948. Okay, it's getting there. They're very close. I'm going to say one thing. If you take this out further and further, you're going to be surprised. This thing almost nails it. You got to take it out a long way though. So that's the reason for that function, why the Q function becomes so interesting, because for the likelihood of the event being very small, you can bound it, and that's the average value, which is very close. So that's the Q function. Let me make a few other comments about this. You haven't found an error function on yours, have you?
I have, yeah.
Okay, well, because the Q function, is related to 1/2 the error function of that over the square root of 2. This one's real easy. This one, almost every calculator has error, it's called complementary error function, pardon me, or the error function. Does yours have that?
I can look. I don't think so. I can't do derivatives or integrals.
No, I mean, let me just take a look at it. It should be in the front pad.
I've had that thing forever.
This is just a calculator.
The only thing I've been able to find is the Bernoulli's
Is there
cycle
another
computation.
term for error function?
ERF or ERFC usually.
That's what I'm trying to,
No, I don't work it.
Out of luck.
I'm not.
I mean, I do know it has the.
I'll stop by the store when we would.
If I was you, in this day and age, just because that calculator is going to stay with you for the next probably 20 years, I still have a calculator from 1991, I think. That when I need a calculator, it's an old HP, but it does everything I need. Get something that I would get like a TI 89 and whatever, a TI. Yeah, I'm not sure of. I think the 89 does about all you want, but the Inspire might be. Is that the best one?
Yeah, because, I mean, the 89, it'll do everything you need, but it's like more, like, command line based, like everything's on one line, and it won't format it, like in the fractions and stuff, make it clean.
Part of the workflow.
I used to use an 89, trust me.
You go for something.
Yeah, this thing is like,
Well, I never used. I mean, I've done HP, and HP, they call it reverse Polish notation, first in, last out. And so it's a stack. It's just like writing programming in, what do you call that? Machine language. All right, so it's basically written for people that do that kind of program. The old HP was my go-to because it would do everything I wanted, and I knew how to use it, and it was easy. I didn't have to learn anything. I mean, it didn't give me the fancy symbolic integrations or anything, but I didn't care for that anyway. But nowadays,
those newer HPs.
I'm going to use that computer. I'm not going to sit around here and learn how to calculate.
There's one HP calculator, control circuits.
I have a feeling in your lifetime, you're going to just be using a laptop or a phone. Because phones these days, you can literally, they emulate everything. You can get MATLAB on there, MathCAD, everything you want.
It's crazy.
There's this app called Mathway.
What is it?
Mathway. You can take pictures of formulas and it does it automatically.
Calculations.
You take a picture of the formula and it'll go through the whole thing. You don't have to click extra buttons.
Show me this. Mathematica was the godsend years ago for physics and people like me, where we had these crazy integrations that would take 5 or 6 pages to do. You could put it in symbolically, and it would do whatever you want. It would do integrations, differentiations, matrix math, and give you the answers. But the answers were formatted in what's called a latex format, so it's perfect for a journal that we publish. So it was ideal.
Go to the journal.
All right. Anyway. Now, here's the deal. For Wednesday, make sure you know, however you want to, calculate these functional forms that we're talking about, because you're going to get problems like that, okay? I'm just letting you.
Talking about Gaussian.
So we can.
Yes, what we just have done, we're going to do some more. These kind of problems, you have to be able to calculate efficiently, not just think about it.
So calculate as an integrate or like use the table, use the calculator?
You can use tables or calculate, but I want a number. I mean, if it's a very rare event, you can use what I just put up there, huh? But if it's not, I mean, in other words, you got to know what you're doing with the calculators. If you know how to use them, it's not going to be a problem.
And you'll give the mean and the variance and
Yeah, yes.
work out from there?
I mean, the problems are going to be similar to the homework problems, and that's the reason I want to go through a bunch. So now the next thing I want to talk about, when we have Gaussian distributions, in general, the central moments and what they are. So I'm just gonna say this. In general, when we have a Gaussian distribution, we talk about moments. Usually it's x, that's a random variable, minus x bar to some nth value. And that bar over the top means it's the average value, expected value of this. So mathematically what this is the integral, if it's a Gaussian distribution from minus infinity to infinity, of this thing right here, which is going to be x minus x bar to the nth power, and then it's going to be times 1 over square root of 2 pi, then there's the variance in there, times exp to the minus quantity x minus x bar squared. Actually, you know what? He does it this way. He doesn't want, he will replace, instead of putting x there, because the integration is going to be with respect to, and the limits are going to, I take it back. It doesn't have to be that. I could have put x minus x bar, my bad, because the limits are at infinity. But when you do it, that's what you're doing. All right? Now, this is called a central moment. And it's the nth central moment. So if you have x minus x bar to the nth power, the average value of that, it's going to be 0 for n odd. And it will be equal to 1 times 3 times 5 times dot 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 n minus 1 times sigma to the nth power. Now I'll tell you why in a second. Sigma, remember, is the standard deviation. Now here's why. Remember we talked about if you have an odd function, the integral of an odd function from minus infinity to infinity or from minus a to a is always 0 for odd functions, right? So if n is odd, this would be like, it would be a function that is odd in nature, and this is even. Odd times even is odd. Integrating an odd function gives you 0. That's the point. So for any n odd, you get 0 for the central moment. That's important. But if it's not 0, if it's an even function, this is for n even down here, and this is in your book. If n is even, then this is going to be the value. Now that's a central moment. It's not the the mean squared value, or it's not the moment of x. This is the central moment, but they're useful. So that's the example. You got to do an example of this. Suppose if we have an example and we want the fourth central moment. Fourth central moment, and that means that x minus x bar, the fourth power bar, would be equal to 1 times 3 times, and then it would be sigma to the fourth power. And that's it. So if I give you a sigma, you can give me that if it's fourth central moment. There's a caution that he has. That fourth central moment, I mean, to get the actual fourth moment, it's more complicated than that. And he qualifies some things, so be careful about these. These are central moments, so you're taking the value x and subtracting the average value from it, and then taking it to a power. Okay, so then, now we're going to do example 2.51 in the book. This is example 2.51. I don't know what page it's on, but
Examples are not the problems with that, in the chat.
no, this is or exercise. Sorry, exercise. Not bad, exercise. Yeah, it's on page 76. So it says a Gaussian random variable has a mean of 1 and a variance of 4. So you know, Gaussian random variable. Mean is 1, variance or sigma squared is 4, mean standard deviation 2. And what's part A for that one?
The probability that the random variable has a negative value.
So what we're really saying is probability of it being negative, which would mean if we use the Q function, it would be Q. Now, think about it. Normally it's X minus X bar over sigma, right? That would be the same thing as the distribution function. We have to replace the Q value with this. So this is the Q function. So this is the Q of 1. I'm sorry, of being negative, did you say?
Yes.
Yes.
All right, so that'd be X equals 0. And let me tell you, so Q of X is equal to the integral of 1 over square root of 2 pi times the integral from X to infinity of exp to the minus u squared over 2 du, right? That's the Q function definition in the book, and right. So, if we take a look at that, if we find the probability of X being greater than 0 to infinity, really what I should say is, take this and find, if we find this probability right here, this Q function, Q of 0 minus 1 over 2, which is Q of minus 1/2. What that is really going to be equal to the probability of 1 minus the probability that it's actually, that the function is going to have a value greater. Let me explain this. See, when I do this, and I replace X with this argument, now I'm saying the probability now I'm calculating of this value being greater than minus 1/2 is the same thing for the Q function that's normalized. The same function of same as calculating the value, probability of X being greater than 0, because I replaced X here with 0. With me? Now, if I take 1 minus that, I get the probability of being less than 0. Does that make sense to everybody? Think about what I'm saying. Do you agree with that?
I agree that the answer,
We're not done. What?
never mind.
No, go ahead, say it.
The answer in the book, is not the 1 minus it, though, it's just the value that you get.
Well, wait a second. That value right there is a Q function, right?
The 0.5.
When, minus 0.5. And that right there, it's going to be, the answer in the book, I can tell you, let me, part A, answer, the probability of X being less than or equal to 0 is going to be 1 minus the Q function of minus 1/2, and that's where you get that. And that should be 0.309. You can check me on that. And I did, because I did this with my calculator, with my laptop, Q function.
It's, 0.5.
No. They jumble the answers. They're not in order. There's 0.30, isn't it?
Yeah, 0.085 is the answer, but it's, the thing I'm confused on is that just 0.5 is that, 1 minus that would be like 0.7. Just 0.5.
No, minus Q of minus 1/2 is, that's one, this right here is one, it would be Q of 1/2.
Yes, that's what,
Yeah,
Q 1/2 is that, but the 1
Yes.
minus it would,
1 minus this is Q of 1/2.
can I show you one?
Yeah.
I think I'm explaining this poorly.
Okay.
The 0.5 is that, without doing the 1 minus. That's what I'm confused about.
Yeah, but, see, this is Q of minus X, right? Well, Q of minus 0.5 would be one minus Q of, well, it's not even 0.5, it's, yeah, it's,
So wouldn't that be one minus 0.3085?
this is, I mean, Q of minus X, right, is one minus Q of X, right?
Yeah.
Alright, so if, then take a look at this, then this says, this P of X less than or equal to 0 would be equal to one minus Q of minus 1/2, which is one minus Q of 1/2, right? I just substituted this for that.
I didn't even plug it in again.
And then, so the ones go away, and you just get Q of 1/2, right? So that should be the right answer.
It is, that's why I was confused, I didn't know you substituted it in again.
You have to on your tables. I didn't, I've got the Q function. So I just punched it in, but you're right. Yeah.
So, could you explain where you got 0 from for x again? I didn't
Remember, he wants it for negative values, right? So I know that there's a Q function right here. Just bear with me now. When I take Q of this, right here, this is the probability of it being greater than, anything great from that point up to infinity, right? I don't want that, I want 1 minus that. I want the probability of it's negative, right? So for negative, then you put x equals 0, right? Now I go from, and when I have x equals 0, the Q argument is minus x bar over sigma. X bar is 1, sigma is 2, so it's minus 1/2. So it'd be this integral right here from minus 1/2 to infinity. But I don't want that, I want 1 minus that, I want whatever's left, that's the reason. Because if you think about the distribution, the way it looks, it's this way. If this is the density function that's skewed, and I'm going to try to do this right, the average value is 1, right? So out here at 1, it looks something like this, right? Now I get my Q function, and I change the argument. It's the same thing as the Q of minus 1/2, which is down here. It's normalized, but I'm integrating from here. What I want to do is find out what this is. That's my goal, right?
Right.
So that would be, and then whatever's left, 1 minus the integral of my f of x here, dx, from 0 to infinity, that would be the probability it's negative. That would be all that area, right?
Right.
Well, that's the same thing as the Q function here, replacing the argument with x minus x bar over sigma. X is 0.
So if you wanted to do,
This, if you just did this calculation, this is the probability of x being greater than whatever value you put there for x. All right?
okay,
With the standard deviation and the mean given, right? That gives me it. If I want it less than that, I take 1 minus that. Let me keep doing these problems because I think a lot of stuff will come with that. So that's the first part. What's the second part of that problem?
The probability that the random variable has a value between 1 and 2.
All right, how do you do that one? Now this is pretty self-evident. Let me do it right here. So now I want the probability from 0.1, is it? Or what?
Between 1 and 2.
1 greater than x, less than 2, right?
Yes.
Remember, that's x. Right? Now, if you want to use the Q function for this, then just think about this now. The Q function itself says the integral from x to infinity. So now, what we want to do is take the value, the probability of this function right here. We're going to replace the argument x by that value, right? From the lower to the upper boundary. So what we're really going to do is this. We're going to take Q, and the lower boundary was 1, right? So we got 1 minus the mean, which is 0 over sigma. So it's Q of 0 minus Q of, and then it's going to be 2, right? 2 minus 1 is 1 over sigma. So Q of 1/2, right, because sigma is 1/2. The variance is 4, that means standard deviation 1/2, correct? I mean, you follow me with variance? Like, variance is sigma squared, is 4, then that means sigma has to be 2, just square root, that's all it means. So if you do that, that should be the value. So this is 1/2, right? Minus, what is this from the tables?
0.3085.
0 point what?
3085.
And I don't know what that is, but
0.1915.
0.191, and you can use tables if you want, but your calculator should be able to do all this very quickly. And that's the reason I'm saying. Personally, I mean, you can use tables if you want. I'll let you use your book for this quiz if you want to use the tables, but frankly, you shouldn't need them.
Yeah, for now, I can scrape by, but probably as I go on, I'll use the calculator more and more.
Yeah, I'll be fair with you guys. I'll give you your open book on this one because of the tables. I'm not gonna copy all the tables down for you. I could, frankly, I just wanna make sure you have access to them. Are you with me on that? Okay, and that's right. This is the last part?
The probability that the random variable is greater than 4.
All right, now, that's beautiful, because we got the Q function. Q function's all about greater than, right? X is great. So now the only thing we do is what? How would you do this problem for part C? What do I do with this Q function now to manipulate it? Where I want the probability of the random variable X being greater than 4, right? So that would be what? Q of simply 4 minus 1 over 2, right? Or Q of 4 minus 1 is 3 3/2, right? Q of 1.5, what is, I'm asking him because he's thumbing at the table.
0.0668.
0.0668, is that in there?
That's the answer in the exercise.
It is, okay. Y'all follow me how to do it?
What page are these tables on?
It's 435, and the feed.
I would tab that
the feed
page.
right before it.
I mean, go get one of those little yellow tabs or something, put it on there, because if you're gonna use those things, you're gonna use them a lot.
A lot.
Until you get a calculator. Calculators will do this a lot quicker, I'll tell you that. You don't have to do any crazy interpolation either. Okay, that's part C. Let me keep going. All right, this is exercise 2-5.2. This is central moment stuff. Where is this? Boy.
Yeah, the tables will, it's a strain on the eyes.
Yeah, you should look at his formula. It's like,
That ain't bad, but
Is it just like a photo or
no, it's literally just do 1/2 times integral from, you have that, whatever's inside the parentheses of Q, that's your lower limit, your upper limit is infinity, and
that's a pretty good thing.
That's an inspire?
do it, yes, so.
Okay. Next,
2-5.2.
yeah. So, what was the first couple of parts? 2-5.2. Can you tell me?
It's going off from 2-5.1.
All right, so mean is 1 and standard deviation is, this variance is 4, right? Go ahead.
For this one, it's the mean is 5, the variance is 16.
Oh, shoot. Variance is 16?
Variance is 16.
Sigma's 4. Okay, go.
The fourth central limit.
Okay. So they're asking x minus x bar to the 4th power, right?
Yes.
Alright, now, this is an even one, so this ain't gonna be 0. So it's gonna be 1 times 3, not times 5, but 1 times 3, and that's gonna be times sigma to the fourth. So that's gonna be 3 times, 6. It says the variance is 16?
Variance is 16, it's going off 2-5.1.
Okay, so that's gonna be 16 squared, right? That looks big, I don't know if that's, what is that? That's a big number. Oh, yeah, that's it, that's it.
760,
Is that an answer?
they don't show that it's this. Oh, you got it.
Huh?
That's what I got, I'm saying, 760.
Wait a second.
We finished exercise 2.52.
It says,
Oh, my
no, 2.5.25, fourth central moment. That's,
I went to the problems one, not the exercise, that's my bad.
as a mean value of 1 and a variance of 4, not 16. Mean value of 1, I thought, that makes
I went
sense.
to the wrong problem.
Yeah. So the mean value of 1, variance of 4. There, that sounds better. Now take a look, this should be the right answer. Then this is gonna be 3 times what? 3 times 16, right, or 48. That should be one of them.
Yes.
Isn't it? Okay, what's the next part?
The fourth moment.
All right, fourth moment, not fourth central one. This is a little different. So for the fourth moment, that's this, right? Now technically, we can actually use the central moment theorem to get this, and I don't know where it is in this book, but this is one of those that's kind of long. It's this, and I mean, you can do it directly if you want to do the integration, but the fourth central moment of this thing, and he has it in his book, is going to be, I thought I had it, yeah, I mean, I've got it, that central moment, the fourth moment, pardon me, is going to be 3 times sigma to the fourth power plus, I'll show you where this comes from, times the variance times the average value squared plus the mean value to the fourth power. I'm going to just write that down for these. This is something where you can get all these things by doing this. When I take a look at the central moment, where I have x minus x bar to any power, say 4, and I want the average value of that. That's the integral of x minus x bar to the fourth power, and then it's going to be times, I'll just put it as f of x dx from minus infinity to infinity. Y'all follow me? That's what it is. I'm not going to write down the Gaussian, but that's what it is. If you look at this and expand it, you're going to get integral, and then you have x minus x bar. That's going to be times x minus x bar times x minus x bar. You can see where I'm going with this. X minus x bar, f of x, right? And then you have a dx. Now, when you do this, the highest order is you got x times x times x times x, that x to the fourth times f of x dx. That's the fourth moment. Do y'all follow me? That's fourth moment. Then what are you going to get left over when you do this stuff? Now take a look. At the end, you got minus x, minus x, minus x, minus x. That's going to be a plus value x bar to the fourth power. You follow me? That's here. This. Then you're going to get all these inner product things that you have to do. You have to square out the thing. It's a pain in the butt to do this stuff, by the way. And you're going to end up getting a bunch of terms, and you're going to collect like ones. And the ones you'll collect, there'll be obviously there's the, just the constant, the x prime. You're going to get an x to the fourth. Then you're going to get an x squared in the middle operator, and you'll see the other ones cancel. And then you can set it up that way and do it. So I don't expect you to know how to do a lot of this, but there's some properties that I'll show you later. This is actually somewhere in the back of the book. All the moments in terms of central moments and average values are given somewhere in there, I believe. I haven't actually checked his book about this, but if you just look up moments defined in terms of central moments. We can find something on the internet, I can post it for you. But all this is well known. So anyway, let's just calculate this value for this one. What does it come out to? We got, for this one right here, we got 3 times sigma to the 4th power, that's 3 times 16, right? Plus, and then we got 6 times sigma squared, which is 4, right? The mean value is 1 plus 1. So that's going to be 48, right? Plus 24 plus 1, 40, 72, 73. That should be one of the answers. Is it? Now he gives us, what I just wrote up there is in the book. There's a third central moment we can do. Maybe we should do it just to show we're not absolutely reliant on tables. This is on page 72 in the middle. He shows the 4th moment in terms of central moments. If you take a look at that.
And where did you say this formula was in the book? Or,
It's on page 72. It's below 2-2.27.
yes.
See? I remember the fourth central moment is sigma to the 4th. Maybe I didn't say that. Like the second, we call the variance, second central moment is sigma squared. 4th central moment is sigma to the 4th. 6th central moment would be sigma to the, it would be sigma to the 6th power. Anyway, for the 3rd central moment, how would you get it? How about we do it right here, this way we can talk about it. Now, what do you know the 3rd central moment is? Then we'll do the 3rd moment.
0.
It's 0 because it's odd, right? So we know it's going to be 0 for the 3rd central moment. So x minus x bar cubed, that average is going to be 0, which is nice. 3rd central moment is this, isn't it? Right? It's just, so if you take this, first if we take x minus x bar, just bear with me. If I have x minus x bar, and I square it, I get x squared, right? Minus 2x x bar, and then plus x bar squared. Agreed? I'm just doing the math on square. Now if I take that, and I multiply it by x minus x bar squared, when I multiply it by x, I get x cubed minus 2x squared x bar plus x times x bar squared, and then I'm going to multiply it by minus x, so then I get minus x squared times x bar plus 2x x bar squared, and then it's going to be minus x bar cubed. I hope you appreciate this. I get 6 terms to that. That's a mess, but hopefully we can see something here. The highest power is going to be x cubed, that stays, right? So I get x cubed. Now, the lowest power is going to be minus x bar cubed, that stays. I got rid of that one, and that one. Now, for my x squared, if you look at this, now the x squared operator has this and this, so it's going to be minus 3x squared x bar that gets rid of that and that. And finally, then I got plus 3 times x bar squared. Y'all with me on that? Now remember, I want this one when I'm all, everything's said and done, and that's what I'm after. So now I put this in here. You can see. I'm not a real fan of doing this, but I'm going to do it this way. So my highest order is x cubed. That's the one I want, times f of x. I'm going to break that off by itself, dx. Minus infinity. And then the rest of them, minus, and it's going to be x minus integral from minus infinity to infinity of x and that's going to be cubed times f of x. I'll just leave this one times f of x here dx minus 3 times x bar times the integral of x squared times f of x dx. And of course, they're all from minus infinity to infinity. I'm putting x bar here because it's the average value. And then that's the squared operator. Finally, it's plus 3x bar, now the x bar is just the average value, it's a constant times the integral from minus infinity to infinity of x times f of x dx. Remember, that's Gaussian distribution. All this is equal to 0, right? The only thing I'm trying to do is manipulate this thing for everybody's sake one time. Follow me? And I had to cube that thing. I had to. Now, follow me. This is the one we want. We want this value. It goes from minus infinity to infinity. What do we have? Well, what is the integral of f of x from minus infinity to infinity? It's 1. That x bar cubed is a constant, right? So that's just x bar cubed. This one is just minus x bar cubed. Now, what's this? X times f of x. Odd, even, right? Integrate from minus infinity to infinity is 0, right? I mean, you all agree with me there. So that goes away. Now, what's this one? X squared f of x is second moment, right? Right? And what is that? What can I replace that with? Remember? That's equal to, if you think about this, x bar, or squared bar was equal to what? Sigma squared plus x bar squared. Do you remember that? Or not? That's from last lecture. If you don't, let's see what it is. This, for Gaussian variables now, I don't want to say that. I guess that's generally true though. Trying to show you where it is. We covered this last time.
What are you checking for?
The second moment is sigma squared, the variance plus the average value squared. I forgot where that was, but I know we did that. This is it's the bottom of page 64. It's he has it a little differently, but he has it sigma squared is equal to x squared minus x bar squared. So it's really x bar squared, or x squared bar. The average squared value of that thing is sigma squared, the variance plus the mean value squared. You see it? Bottom of page 64. Y'all with me?
I see a whole bunch of stuff. Oh, never mind, yeah.
Right at the bottom there, we have x bar squared. That's the second moment minus 2x bar x bar. That's just
The second one minus the mean.
yeah. And then what he does is he takes that and he's going to set it equal to what he's got there, and that's exactly right. So here's what happens. I erased that right here. Okay. So this should be sigma squared plus, right? Plus the mean value squared. Y'all remember that? Now here's what I'm getting at. These two values are both negative, they go to the other side. So what happens is the third moment here would be equal to the actual mean value cubed plus, and then it's going to be 3 times the mean value, and then it's going to be times the variance, which is 4, right? plus the mean vector, so I just put a 4 in here, plus the average value, which is 1, and that should be this cube, the third centimole, so that's gonna be 1 plus 3 times 1 times 5. So that, is that 15, 16 in there? Does that answer?
There's one that's 13 and 73. Maybe not 73.
No.
Yeah, 13 is the answer for this one.
What did I mess up? I messed up something, but that's how you end up doing it.
Should that be minus the x bar squared? Isn't it, variance minus, x bar squared?
Wow. This is equal to sigma squared plus x bar squared, right? It wasn't, I thought that was, I might be wrong about this, but I thought this was x bar.
The book says, the variance minus, the mean squared for the second one.
Where are you
Bottom
looking?
of page 64, are you pointing out?
That's mean squared, right? Alright, that's equal to,
The variance, right?
there's a variance, take this to the other side.
Oh, my bad.
Yeah. It's behind. But that, I mean, I don't know if I erased something there, but this is the way you do it, by the way. If we just look there. If we can get this. All this is gonna be equal to 0. We know that, right? And this is all times the density function. Just take a look at this. We want this right here. We want that value, and it's all times densities integrated. If you look at this, what's left over? Well, this one goes away because it's x times the density function. That's linear, so you get this. Now, if I want that, I take that to the other side. It's negative, so that's going to be, yeah, that would be, the mean value is going to be 1 cubed. I'll just put it here. It's going to be x bar cubed minus, and it's 3 times x bar, which is 1. I'll put it times x bar, which is 1. And that's x squared, and so that should be sigma squared plus, I mean, this would be the average right now, plus the mean value squared. Plus, and that should be square. Let me just hold on for a second. That's 1 plus 3. X bar is 1. Sigma squared is 4, right? And x bar is 1, so it's 4 plus 1, that's 5. So that's 15 plus 1. How did you get a negative there? I'm gonna have to check that. But the way you ended up having to do it is you have to take like this to the power 3 and then expand it and see which things which things cancel, and you gotta group terms, but that's the way you have to do this one. Okay. And I'll get back to you on that one. I'm just about out of time. I am out of time. I'm just gonna mention this. I'm trying to do as many problems and talk about problems as possible. I'm gonna go through the Rayleigh distribution next time. All right, if you can, read ahead for the Rayleigh and Maxwellian distribution, will save me some time. I'm gonna give you problems, and the problems you get are gonna be like the homework given last time and this time, okay? And please make sure you can do the calculations, and I'll give you the tables. I'm not trying, there's one thing I'm trying to do is help everybody understand this, and I know this is, it's anything but clear. But you know, you're getting at least a handle on the tables and what the problems are like.
Can I practice for that? There's so many.
I don't know how did I mess that thing up. I thought I had this